Hello, Physical Science. This is Mr. B. We're continuing on with Section 2 today, and the title of this section, again, if you remember, is the structure of an atom. And if you remember from your last video, we simply went over what a proton, neutron, and electron are. Those are the three subatomic particles. And so what this video is going to tell us are some characteristics that different elements have based off of the type of atoms or the number of atoms that they have, and maybe even smaller, even what type of, how many protons, how many neutrons, and how many electrons are within each atom, and how they can kind of determine different characteristics for elements. We're going to talk about things like atomic number and mass number, and how protons, neutrons, and electrons factor into that. And so to start, again, we have our question as usual. It said, how are atoms of one element different from atoms of other elements? And they have different numbers of protons. So that is going to be one of our big distinguishing characteristics, sorry, can't talk here, of our different elements. So if you have 2 protons, you're going to be a different form than an element that has 15 protons. So that is going to be one characteristic, or one important thing why we need to know about subatomic particles, because they will help us distinguish between different types of atoms. And one way that it does this is through something that's called the atomic number. So I'd make sure I wrote down what the atomic number is, and it is the number of protons in an atom of that element. So it's pretty simple. So an atomic number is assigned to each element. And the next chapter, again, I think I've kind of mentioned this, we're going to talk about the actual periodic table of elements. So that'll kind of tie in more to that. But just for now, we need to know that an atomic number is simply the number of protons in an the number of protons in an atom of that element. And all atoms of any given element have the same atomic number, so that means each hydrogen atom has 1 proton in its nucleus, so therefore hydrogen is assigned the atomic number 1. So every single hydrogen we're ever going to see is always going to have 1 proton, and so therefore it is always going to have the atomic number of 1, and then each element has a unique atomic number. So again, and if you look back at that periodic table, you notice they're arranged from 1 to 100 something. I can't remember off it, like 117 something, actually probably a little bit higher by now. And the reason why they have those numbers is because they all have different numbers of protons, or a different atomic number. So that's all an atomic number is. It's the number of protons that are within the atom of different elements. And then again, here's some more examples. The atomic number of sulfur is 16, iron is 26, silver is 46, and that is simply because if we looked at the nucleus of each one of those atoms, sulfur would have 16 protons, iron would have 26, and silver would have 47. So that is the atomic number. Again, simply just the number of protons. And then, okay, so make sure I didn't skip one here. Okay, and so atoms are neutral, so each positive charge in an atom is balanced by a negative charge. So that means the atomic number of an element also equals the number of electrons in an atom of that element. So we've talked about this, again, briefly, kind of based off of some of the experiments that people ran. We know that overall, the atom does not have a charge. Overall, it is neutral, because for every proton we have another electron. So atomic number could technically be the number of electrons as well, because hydrogen has an atomic number of 1, so it has 1 electron to balance out that 1 proton. Sulfur has an atomic number of 16, so sulfur atom has 16 electrons as well. So in everyday atoms, they have an electron to balance out every proton, because overall an atom does not have a charge. So this is pretty important right here, that atomic number could also technically represent the number of electrons as well. So that is atomic number. Pretty simple. It's just the number of protons that are in an atom of an element, and then technically, again, since they're neutral, it is the number of electrons as well. And we also have something when we talk about subatomic particles here called the mass number. So I definitely write this down too. And again, it sounds similar, but they are very different. So the mass number of an atom is the sum, so that tells us we're going to add, of the protons and the neutrons in the nucleus of that atom. So to find the number of neutrons in an atom, you need the mass number of the atom and its atomic number. So I would make sure I wrote all of this down. And we're going to see in an activity that we do tomorrow that atomic number is also another word. They're going to have, or I'm sorry, mass number. They have a different term for that we're going to use tomorrow that's called an atomic mass, but they are all the same thing. And that's just that when you add the protons and neutrons together, and so to find the number of neutrons, we take our mass number and we minus the atomic number, because remember our atomic number is our number of protons. And these two numbers are given on the periodic table. This is listed for each one, and again, once we take a look at the periodic table, this will make more sense too. So we'll actually be able to see that right here is where the mass number is always listed, and right here is where the atomic number is always listed. And the atomic number of aluminum is 13, and this is just an example here. And an atom of aluminum that has a mass number of 27 has 13 protons and 14 neutrons, because again we took that 27, this 27 right here, we plugged it in for mass number, so we took 27, we plug it in for the mass number, we take 13, type it in for the atomic number, 27 minus 13 gives us 14 neutrons. So I'd make sure I have, a lot of this is pretty important, so I'd make sure I wrote this down. So in our typical atoms, we have atomic number and mass number, and they're just the number of protons, and then the mass number, we add protons and neutrons together, and so to find the number of neutrons, we take the mass number minus the atomic number. So I know that's confusing. I know there's a lot of numbers and atomics thrown around here, so just try to make sure you write these down to make sure we keep them straight. And so to finish this section, we kind of have a little bit of kind of an interesting example of when these numbers of when these numbers of neutrons start to change within different types of atoms. And that's when we have something that's called an isotope. In an isotope of an element, they have the same atomic number, and so that means they have the same number of protons, but they have different mass numbers because they have different numbers of neutrons. So when we have an isotope, and we'll get some examples here in a second, but it's basically two of the same elements. They have all the same number of protons, so they're still, again, they're all both hydrogen, but when we look at their nucleus, they have different number of neutrons, so they have a little bit different characteristics. And again, I would make sure I wrote this down, that isotopes are atoms of the same element that have different numbers of neutrons, and therefore they'll have different mass numbers. And to distinguish one isotope from a number, they're referred to by their mass numbers. And we'll give an example here. So for example, oxygen has 3 isotopes. We have oxygen 16, oxygen 17, and oxygen 18. So what that means is that oxygen 16 has a mass number of 16. Oxygen 17 has a mass number of 17. Oxygen 18 has a mass number of 18. And the reason why they have those different numbers is because they all have a different amount of neutrons. Oxygen 16, well, again, we might not know this yet, but oxygen has an atomic number of 8, so that means there's 8 protons. So in oxygen 16, there's 8 neutrons. Oxygen 17, there's 9, and in oxygen 18, there's 10 neutrons. So we get the 10 plus 8 equals 18. And all 3 of these oxygen isotopes can react with hydrogen to form water or combine with iron to form rust. So there's really not a ton of differences between these 3 isotopes. They can all do the same basic things, and they're all pretty similar. And that's the case with most elements. With most elements, it's hard to notice any differences in the physical or chemical properties of their isotopes. So for the most part, that extra or maybe one less neutron isn't going to do much. However, hydrogen is an exception to this rule, so the different isotopes of hydrogen will react differently, because we'll see here with this example. So hydrogen 1, again, hydrogen is the very first element, it has no neutrons. So it just has 1 proton in its nucleus. And then hydrogen 2 has 1 neutron, and hydrogen 3 has 2 neutrons. So again, the reason why this has 1 neutron and it's hydrogen 2, because you take the 1 neutron plus the 1 proton, and it gives you hydrogen 2. And because a hydrogen 1 atom only has 1 proton, adding a neutron doubles its mass. So because hydrogen is so small to begin with, because it only has that 1 proton, when we add that 1 or 2 extra neutrons, it's either going to double or triple its mass, because remember, a proton and a neutron are about the same size. So when the element or the atoms of the elements are this small, when you add an extra one to it, it's going to create quite a big difference there. And then to wrap it up, again talking about the difference between these, water that contains hydrogen 2 atoms in place of hydrogen 1 atoms is called heavy water, and hydrogen 2 atoms have twice the mass of hydrogen 1, and so the properties of heavy water are different from the properties of ordinary water. So I would just maybe take a quick look at this chart, and it shows us how boiling, or the melting and boiling points, and the density changes just by having a different isotope of hydrogen when it forms water. So that is, again, hydrogen is one example where the isotopes actually have different properties and can maybe actually play some type of effect. So that is it for section 2. Let me know if you have any questions.